All right, so welcome everyone. Hello, and welcome to the class Generative AI with Stochastic Differential Equations. As you all know, this is an IAP course. It's going to take place in the next 2 weeks, and we're going to focus on giving you an introduction to flow and diffusion models. I'm Peter. I'm a PhD student here at MIT, supervised by Tommy Jakola and Regina Barcelay, and I'm co-teaching this class with Ezra. You're going to raise your hand. So we did this class together, and you see both of us in the next few weeks. At this point, a quick shout out to Tommy, who sponsored this class and advised us with the design of the class. So we're all here, I guess, because we've all witnessed a tremendous revolution of AI systems happening in the last few years, what's commonly called generative AI in layman's terms. So for example, you've seen artistic images like from Stable Diffusion or Midjourney. You've seen realistic videos being generated from video generators like Sora from OpenAI, or you've seen things like ChatGPT that you use potentially every day to draft text. So the really distinguishing feature of these systems is that they're creative. Like previous AI systems were mainly used to like predict things, for example, like classify an image. But these systems, they generate new objects. And this class, very high level, teaches you algorithms to generate objects. So that's the goal. And we're not focusing on arbitrary algorithms, but we're focusing on what's called flow and diffusion models. So the specific family of algorithms, like there's a whole family of related frameworks, and all of them basically build a state-of-the-art models for generating images, videos, or proteins, and a variety of different modalities. For example, you've heard potentially of Stable Diffusion or DALL-E, which are based on these models. Potentially heard of OpenAI Sora or Meta's Movie Gen. And even in the scientific domain, things like AlphaFold 3 or RF diffusion, they're all diffusion models. So these models are really at the core of a lot of generative AI models, and the goal of this class is to make you understand them. So flow and diffusion models, given their name, they're based on a bit of theory, and we believe that to understand that, you really need to understand the theory first. And so along with this class, you will be taught about ordinary and stochastic differential equations. We basically want to give you the necessary mathematical toolbox to understand these things. On the other hand, we want you to implement and be able to apply these methods. So that's what's going to be happening in the labs. So see this class as has 3 goals. You learn flow and diffusion models from first principles. You learn the necessary amount of math, but only the minimal amount of math to understand them. And third, you learn how to implement and apply these algorithms. Quick overview. So we start off today, the lecture 1. Today we're going to talk about sampling. So we're going to formalize what it means to generate an object. Next, we're going to construct flow and diffusion models. So we're going to learn what they are. The next thing, we're going to learn how to derive training targets for them. So every training algorithm has a certain objective. We're going to learn what the objective is. Then we talk about flow matching and score matching, which are the fundamental training algorithms. That's going to be on Thursday, so that's going to conclude week 1. And next week, we're going to talk about how to build image generators. So we're going to, on the example of things like Stable Diffusion, we're going to learn about network architectures, how to condition on specific prompts. We then talk about advanced topics, for example, like alignment, how to deal with complex data types, how to distill a model. And then on Thursday, we'll have a guest lecture with, where we will focus on 2 new applications of diffusion models. The one is protein design, where Jason from MIT is going to come, give a great talk about how he was really pioneering the design of diffusion models for these applications. And also in robotics, where Benjamin Burfield from Toyota Research Institute, who's the manager there, who currently leads really the frontier of diffusion models in the application of robotics. Great. OK, so let's start off with section 1 and think about like what it means to generate something. So we will see we're going to go from generation to sampling. So the first thing is, how do we represent the objects that we want to generate in a computer? So that should not be totally new to you, but let's just recap. So for example, like an image has a certain number of pixels, it has a certain height and a certain width, and usually have 3 color channels. So numerically, we represent this object as a vector set that's in the vector space, or it's a vector of length h times w times 3. So usually we can represent that like that numerically in a computer. Videos are basically a stream of images. If you have t time frames, each of this image represents an image in itself. So you usually can represent this in the computer as a vector of that shape where it's like t times whatever the size of the image was. Let's think about, for example, a molecular structure. Molecular structure, let's say, has n atoms, and each atom has 3 coordinates. And you would represent that as a vector of that shape, where it's basically each row corresponds to the coordinates of a specific atom. So all of this is to say that in this class, we want to represent the object we want to generate as vectors. There's other ways of representing, but in the end of the day, what we want to generate mathematically is just vectors. Let's think about what does it mean to successfully generate something. So let's think about it. We have a prompt, a picture of a dog. And let's say you have these 4 images that you see here on the right. So the first one is just some noise, maybe something you've seen on an old TV. How would you describe this? That would be completely useless, right? That has nothing to do with what we actually want. Let's say this image, it's not a picture of a dog, but at least it looks like something, it looks like an image that we would have done in real life. Okay, so it's bad, but better than the previous one. This one is at least an animal, but it's the wrong one, it's a cat. And finally, we get a dog. So you can see you rank these images based on how good they are and how good they align with the prompt. But these are subjective statements. Like when I say, oh, this fits better, it fits less better, that's not a statement I can mathematically formalize. So the question is, how do we formalize this? And the language we use, and everybody in generative modeling use, is the language of probability theory, where we basically introduce this object, what's called the data distribution. And it basically converts the statement of how good something is to how likely something is on a specific data set. For example, in this example, we could say, how likely are we to find this picture on the internet? So let's say we have prompted the picture of the dog. It would be almost impossible to find a picture like this with this caption, right? This would be pretty rare. This would be unlikely, but maybe there was a swap between animals. And this would be very likely. So we're basically translating how good an image is to how likely it is under the data distribution. It's basically, we translated this subjective statement into a statement of probability theory. So let's think about what this means formally. So I just said we have a data distribution that essentially is the distribution of objects that we want to generate. And throughout this class, you should keep this notation in your mind. It's called p data. That's the data distribution. Now let's think back about how we represent probability distributions. The usual representation, the one we are going to use here, is the one of a probability density. Basically says that p data goes from the vector space R to the D, which is our space of objects, and gives you a non-negative number. So given an object set, it gives you a likelihood or probability of how likely that object is. I should stress, we don't know this probability density, but we just postulate it as a distribution they want to sample from. So what does it mean to generate something? It means to sample from this distribution, to roll the dice and get samples from this distribution out. And hopefully, if we've done this right, what we will get is an actual good image. So an image of a dog, or at least most of the time we should get that. Good. But we don't just want to do that somehow because we're doing machine learning. We need some sort of like data, right? So the question is like, how does the data set fit into this picture? Let's think about a few examples. For images, we could just use publicly available images from the internet. We could just pull them and like collect the data set. For videos, we could just use something like YouTube. For protein structures, we could use something like the Protein Data Bank, just generally scientific data that's been gathered over the last few decades. And what's a data set? A data set consists of a finite numbers of samples from that data distribution. So we just denote this as set 1 to set n, which are just samples from the data distribution. And we're going to use that to train our model. All right, so let's think about something like the case I just described to you was what's commonly called unconditional generation. So usually we have one model for, let's say, a fixed prompt. For example, that prompt could be dog, and it basically means that you always get the same image from the same model, right? You would always get images of dogs. They would likely look a little different, but at the end of the day, they would all be images of dogs. What we more want is we want to condition whatever we want to generate on a certain variable that throughout this class is going to be called y. So for example, it could be y could be dog, could be cat, could be landscape, could be a much more complicated object. It could be a room full of MIT students listening to a diffusion class. So something like it could be a much longer text. So we want to have this variable y basically condition our generation. And for this, we introduce this object, what's called the conditional data distribution, which we denote as p dot dot stands for a placeholder, given y. So it basically means, given this prompt y, what's the distribution of the data given this prompt? And conditional generation essentially means that sampling from this conditional distribution. So we sample an object z from p data given y. And it's important to note that this is the case we're going to focus on first off, because like most generative modeling frameworks start with that, and then they translate it to this case. So this is the case we're ultimately interested in. But we want to first focus on this case. So just keep that in mind, that where we're starting and but where we're going. All right, good. So let's think about a generative model. So given its name, a generative model tries to generate something, which we've just learned means sampling from the distribution. So in other words, a generative model tries to generate samples from the distribution. And usually what we have is what's called an initial distribution. We call this here as p init. It's an important notation as well that we use throughout this class, which is essentially the initial distribution. And in the default case, you could always think about p init as a Gaussian. So as a standard Gaussian with zero mean and a diagonal identity matrix as covariance matrix. So that's what's here on the top right. And the idea of a generative model essentially start with an initial distribution. So you sample from a Gaussian, which visually would just look like white noise for an image. And what you get out is you get an image of a dog. So essentially, in the language of probability theory, a generative model converts an initial distribution into a data distribution. And the goal of this class is to teach you how to do that, and not just somehow, but with flow and diffusion models. And that's what we're going to talk about in a second. All right, I'll stop here real quick. Are there any questions? Good, cool. All right, so let's dive right in. So as I said, we want to build generative models with flows and diffusion. And the goal of this section is going to be to define what that is and how we sample from it. At this point, a quick note. So I'm going to write now on the blackboard, but there's lecture notes online, which is a self-contained summary of what I'm going to tell you here. So you're very invited to take notes along, but I also want to just, as a disclaimer, use the lecture notes. That's what I would do.
Go to the class website, diffusion.csil.mit.edu. There's a huge conspicuous button that says class notes. Click on that, go to the class notes discussion. So feel free to follow along with what you're saying.
Thanks. All right, cool. So let's get started. So we're going to talk about flow and diffusion models. And throughout this class, we will always have a flow component and a diffusion component. And it's much like the most important thing is you understand the flow component, because it's really the basis for the other part. So I would almost say like the flow component is the one that's really core to understand. So if you struggle, make sure you understand the flow component and then maybe revisit the diffusion component. Okay, so let's start off with thinking about what's the fundamental object of a flow. And that's what's a trajectory. So I'll first define what a trajectory is. A trajectory is what intuitively think a trajectory is. It basically is a function of time. And in this class, we're mainly going to focus on time from 0 to 1. And it essentially, given a time point t, gives you a vector xt. So you're basically saying for every time point t, I'm getting a vector xt out. And the way to think about this is essentially in 2 dimensions, for example, you would have a point, and you're basically moving through space, and that's basically your trajectory xt. The other fundamental object is a vector field. And a vector field we commonly denote here as u. And it has a spatial component and a time component. So we have a vector x at time t, and it returns a vector ut of x. Visually, you should think about a vector field as something that at every point in space gives you direction. So like, let's say you start like at this point, it gives you direction here. At this point, it gives you direction here. It basically gives you directions at every point. And you basically, the idea is later to follow along this. So let's define now, and that's very fundamental, what an ordinary differential equation is. An ODE, which stands for ordinary differential equation, which you might have also heard before, is basically describes conditions on a trajectory. So the first thing we have is that a trajectory should start at a specific point, which is called the initial condition. So x0 should, like capital X0 should start at lowercase x0, which is what's called the initial condition. And then we have the condition that we're basically saying that we want to follow along the vector field that's describes the direction. So let's say we started here at x0, and we basically follow along the time vectors across time. You should keep in mind that these directions change over time because the vector field here is time dependent. But basically, you should think about it's basically following along the direction specified by a vector field. So how do we describe this? We're basically saying that the derivative or the velocity of the trajectory is given by ut at the location where xt currently is. So it says the direction of xt is given by the location of x and then specified by ut. And that's what's called an ODE, or combined with the initial condition, it's called an ODE. Maybe some of you have heard this. I mean, ODEs are fundamental in mechanics, in engineering, in physics. So I'm sure you have heard this in some form or another before. But this term is less common, and it's called a flow. So a flow is essentially a collection of trajectories that follow the ODE. So essentially, we gather a lot of solutions for different initial conditions, and then we gather them all in one function, and we call that a flow. So let's define what a flow is. We commonly call this psi. And like before, it has a spatial and a time component. And then given an initial condition, x0 and t, it maps it to psi t x0. And what we're basically saying is that for every initial condition x0, I want this to be a solution to my ODE, which essentially has the following condition. It means the initial condition says psi t of, psi 0 of x0 is just x0, which is essentially this condition. So we're starting at x0. And the other component is that the time derivative of psi t of x0 is specified by this equation. So it's specified by psi t of x0 and ut. All right, just to recap. So a flow is essentially a collection of solutions to an ODE for a lot of initial conditions. So maybe like as a diagram. So an ODE is defined by a vector field. So a vector field defines an ODE. A trajectory is a solution to this ODE. And then a flow, a flow is a collection of trajectories for various initial conditions. So a vector field defines an ODE in this format. A trajectory, xt, is a solution to this ODE, and a flow defines a collection of solutions to that for various initial conditions. Good, cool. Let's look at an example. So what you see here is an example of a flow, and that's a visualization that takes a bit of time to get used to. So in blue, you see the vector field, and then in red, you see for every grid point, that's an initial condition, and you see how this initial condition moves through space. So the grids, how they get deformed, is It's basically a visualization of the flow. So basically it says, now that's a flow map, and every time there's a new psi t for a different t, and it kind of moves through time. Good. All right. So the first thing we should ask ourselves if we see an equation is always, does a solution exist? And if yes, is it unique? And we can answer this question with yes under certain regularity condition. So if the vector field ut is continuously differentiable with bounded derivatives, then a unique solution to this ODE exists. There's a bit more general condition, which is when the vector field is Lipschitz. If that's not a term for you, it doesn't really matter. In this case, the key takeaway is, in all practical interests of machine learning, a unique solution to this ODE exists. Actually, in most classes you've ever taken, that already was implicitly assumed. I'm just going to restate it again, that there are certain nice conditions you need to assume, but these conditions are usually the case in the case of machine learning. If this would be a math class, you would prove this. Maybe you've seen this before. It's called the Picard iteration. I'm not going to do this, of course, just for your information. Good, cool. Let's think about an example. So a very simple example is a linear vector field. So ut of x would just be minus theta times x. So you just multiply a vector x with a scalar. And that scalar we assume to be bigger than 0. So we take minus theta of x. And the claim I'm going to make is that the flow is given by this function here. So some exponentially decreasing term times x0. And visualize it's here on the right for different initial conditions. So you should see here the y-axis starts at different initial conditions, and it exponentially decays towards 0. So I make the claim that this is the flow. So what do I need to check? I need to check that the initial condition holds. So t of 0, that should be 0, is exponential of 0, which is 1. So this is just x0. So it starts at x0, so the initial condition is fulfilled. And to show that the ODE is fulfilled, what do? We just plug it into the equation. So we take the time derivative of psi t, and then we can use the chain rule and plug in the definitions again. In the lecture notes, this is explained in more detail. But you show that basically you see that the first and the last equation is essentially this condition. So you see that the ODE is fulfilled, and this is the flow that we want. Cool. OK, so unfortunately, in most cases, it's not that easy. You cannot just find by hand a solution to an ODE. And what we do is we need to simulate it. And most of the time in this class, we're going to use a method called the Euler method. And that's basically, the idea is that you just simply go into the direction of the vector field for a small time step at every time. So let's think about what this means. We get a vector field ut. We get an initial condition x0 and get a certain number of steps. And here I assume that we just simulate it until time 1. You could also use another time. We start at time 0. The step size is just 1 divided by the number of steps. We set the initial condition. And then we just, at every time step, xt plus h updates the previous time step plus h times ut of xt. So we just basically at every time go a small direction into the direction, small step into the direction of the vector field. And at the end, we just return a trajectory. So that's numerical simulation of an ODE that many of you had potentially have seen before. Good. All right, so let's now use this for machine learning. So now the question is, where does the machine learning come in? And here we want to use a flow model, which basically leverages what I've just told you. So what was our goal? I told you that a generative model converts an initial distribution, P init, and does something I haven't specified yet. And what we get out is the data distribution. And given what I told you, it will not be a surprise to you that we want to do this transformation with an ODE. So what we're going to do is we're going to start off with the initial distribution. We simulate an ODE, and then we get a data distribution, hopefully, out. So let's start with a neural network. And the idea is basically that really what defines this ODE is a vector field. So let's just make the vector field a neural network. So we have a vector field ut theta, which is, as I just defined, a function of time and space. And theta are the parameters. So I'm not telling you what these parameters are at this point because it doesn't really matter. All that matters is that it's a function that is a vector field that has some parameters that we can optimize over. We will talk later about architectures. At this point, it's not yet that relevant. Yes?
So in this context, P init is a vector or a function that converts from a vector to a number?
You said P init? So P init is, at this point, a distribution. You could think about it as a Gaussian distribution. Like for the first few classes, you can always think about P init as a Gaussian distribution. Yes, yes. So we start with something very simple where we have full access to some knowledge, and then we want to end up with some abstract object that we have not yet, don't know yet. So that is more a specification of a goal, less so of a definition. So we want to build something that does that. It's a distribution, so you can sample from it. So you could, for example, you could sample a Gaussian distribution from it, so some Gaussian noise. If you think about it as a probability density, you're right in the sense that given a vector, it gives you a non-negative number that specifies the likelihood of that point. Good, cool. So now what we want to do is, like, an ODE is something deterministic. So at this point, we will not be able to generate a whole distribution yet. But what we're basically doing is we're making the initial condition random now. So what we're saying is x0 is sample from P init. And thank you for that question, because it basically means I told you P init is something we know, something we specify, something we design. So in this sense, we could just, if it would be a normal distribution, you would go to a certain Python package, PyTorch, and just sample, click on it, give me a sample from a normal distribution. So that's something we can easily do. And now what we do is essentially we have an ODE that is like before. So the time derivative of the trajectory is given by ut theta of xt, which means we're simulating this. And what is our goal? And that's going to be really, that's what diffusion and flow models are all about, is to say that the endpoint x1 has the distribution p data. All right, any questions at this point? All right, good. So let's think a bit quickly about a toy example. So we said we want to convert an initial distribution into a data distribution. And now this is, as I said, a toy example. So we have here now visualized a 2D distribution. So if you think about a distribution as a density function, you basically see here the contour lines of that distribution. And we start off with some Gaussian noise, which is visualized here now in 2D. If you would do this in higher dimensions, you would just get some like image like that, which we call x0. So we initialize. And then our goal is to transform it to this data distribution with a vector field. And the first three classes is basically going to teach you how to do this. And the outcome of this is going to be exactly in this toy example this. So I told you that in red you see a flow. And in this case, this flow is simulated with a neural network. And it converts, as you see, initial distribution, a Gaussian in this case, into some data distribution. And you see that at the end. So now we're ending up with the distribution that we wanted. And of course, we're going to do this in much higher dimensions with high resolution images later. But for this, the mathematics, the model is always the same. So there's no real difference in the sense that what it actually does. So how to generate objects with a flow model. So what are we going to do? Oh, yeah, question. The red grid is the flow. So you could think about the red grid as initial conditions. So let's think about it like the bottom left point of this plot. So this one, it just basically over time moves in this with this left grid point. That's basically how it moves through time, and basically it warps this distribution into one that we want to have. I've not told you how to do this yet. This is our goal, right? So like at this point, we've just randomly initialized the model, and it's just nonsense. But like this is where we want to go. Oh, yeah, your question was what the vector field is. So the one in blue. The red one is the flow, the blue one is the vector field. Okay, cool. So now, this might seem now not so hard, or might seem obvious, because I'm just restating something I've said before. But this is important because you're going to need to implement this. And that's basically how we generate objects with a flow model. So if I would now give you a flow model, let's say Meta's movie generator, that's a flow model, you would know now how to sample from this model. We're basically initializing randomly with our initial distribution. We draw a Gaussian. And essentially what we're doing is we're looping over our Euler scheme. So basically at every time step, take a direction that's specified by our neural network. So we basically, every time we evaluate the neural network ut theta at a point xt, we get some vector out of it, and we update our previous step with this vector field. That's the sampling algorithm. The sampling algorithm is rather simple. The training is going to be much harder, but the sampling is basically that. And what we return is the final time point. Maybe that's important to note that, like, that's what we're going to end up with. Good, cool. That's it for flow models. And now we're going to go to diffusion models. I'm going to pause briefly, make sure that we're no questions, all good. So you can always ask questions. Just raise your hand if you want. But sure, question. It's the second thing. It's the direction. It gives you basically the change. It's the velocity that you have at a specific place and a specific time. Good, cool. Yeah, another question? For that vector field? So you mean what this notation means? Oh, yes. I guess I haven't told you yet. All I'm saying is that for every parameter, you can think about a parameter as a vector of, like, let's say length k, but k doesn't really matter at this point. It's just some numbers that specify how I transform my input to output, which in this case means specifies the vector field. And there's going to be a diversity of different architectures. It's just that this architecture usually differs by modality. For images, for videos, for proteins, all of this will, the neural network architecture will differ. So we're going to talk about this once we talk about specific applications. Yeah. So you asked about boundary conditions. So a boundary condition is usually something that exists for partial differential equations, or PDEs. In this case, an ODE is also a partial differential equation, but a boundary condition is the initial condition. It says the boundary at this point would be the time, like time 0, which is the boundary of the time length line, would be x0 equals x0. Yes, yes. Oh, you mean why the red, so your question is, why does the red grid is not defined under whole space anymore? Because, so what we're starting off with is with red grids populated across the entire space, but they then change over time. So there's still going to be a value that you can evaluate, but the initial points that have been specified by this red grid have moved in the meantime. I would not say that's something that I would not say that's a Lagrangian few. More like, yeah. Yeah, there's infinite, like you say that definition, the set where this function is defined is infinite in that sense. Well, you know, if you're in a computer, you have numerical precision, right? There's like limits, but for this purposes, like it's fine on everywhere. Cool, okay. So let's go to diffusion models. And diffusion models essentially extend the ideas that we just discussed, but to stochastic differential equations. So to do that, we first need to define what a stochastic differential equation is, which is going to be most of the work now that we have to do. Yes. Yes. That's a great question, actually. So what we are specifying, the neural network, the model, like your PyTorch model or whatever you want to implement, is going to be a vector field. So in that sense, I don't quite like the terminology flow model, because the neural network itself is the vector field. That's something important to keep in mind. The flow is the map that we implicitly get by simulating this ODE. So like I told you before, that a flow is basically a function that solves this ODE. So the flow map would be abstractly defined as whatever output map, like output x0, I map to psi t theta of x0. Now what psi t theta is essentially the flow that corresponds to this ODE. So that's a flow model in that sense. But we've not represented this as a neural network. We've just represented an algorithm, which is this algorithm I've just showed you, that implicitly computes this map. Yeah, great question, because and there are also models that explicitly parameterize the flow, but they're less popular nowadays, because it's a bit hard to do so. Good, cool. So diffusion models, think about, they use stochastic differential equations, and we basically do the same game as before. So we're going to now think about what a trajectory is. And why? Because diffusion models are not inherently deterministic like ODEs. Their solutions are not trajectories, but random trajectories. And the language that we use for random trajectories is that of a stochastic process. So you should think about a stochastic process basically as a random trajectory. So what's a stochastic process? So we have a random variable xt, where in this case, t is bigger than 0, and in most cases, it's going to be from 0 to 1. So you can have any time convention here, but like most of the time, you're going to go from 0 to 1. And essentially, we have the same thing as before. So we have a trajectory x that is a function of time, that goes from time to RD and maps a time step t to a xt, which is a vector. But in this case, we can draw samples from x. So x itself is random. Okay, so stochastic process is a random trajectory. And that's important to keep in mind. How to visualize this? Same as before. We start off at some point, and then we go through space, which would be a trajectory. There would be one draw of that stochastic process. Now we do another draw that might look slightly different. So stochastic process, if I do the same trajectory twice, I might get out something different. It's important to keep in mind. There's no one trajectory that we're following here. So the collection of these trajectories, or more like how likely they are, that's a stochastic process. All right. So the other ingredient we need is what's called a vector field. So I don't need to define this anymore. I've just done it. It's the same thing as for ODE. So the key ingredient will be the same, which is a vector field U that looks exactly like before. It has a spatial component and a time component, and it returns a vector. So this is basically what we've done before. So a vector field we've already seen. And there's now, though, a second component, and that's new. And that's what's called a diffusion coefficient. And what's a diffusion coefficient? In this class, we're always going to call it sigma. And it's being a function of time. So it's like for every time, it gives you a value. And it gives you a value that's a real number. So for every time, you get a value sigma t. And that's what's called a diffusion coefficient. You can make this also more complex. But at least in machine learning, most of the time, this object is like this. And the idea of the diffusion coefficient is basically we're injecting randomness or stochasticity into our ODE. That's basically what the role of this diffusion coefficient is. I should say that this is bigger, this is non-negative. So if sigma would be 0, we would not inject any noise, we would not inject any randomness. If sigma is very large, we inject more noise. And now I'm going to write down what a stochastic differential equation is. It's not going to be clear exactly what it means, but I at least want to introduce the notation. Okay, good. So the same way as before, we will have an initial condition. So we say that our trajectory, or in this case, stochastic process, is going to start off at x0. But now something different comes in. So maybe I should say, you could also make this random. So you could also make the initial condition random again. In this case, we're just going to have a fixed initial condition. But this condition just says stochastic process always, for every draw of x, will start at x0. And now the SDE has, so stochastic differential equation is a bit long. So people call it SDE. So whenever I say SDE, I mean stochastic differential equation. And the notation that we use here is, let me make this very clear. We're going to use what I call like the dx notation. That's the symbolic notation. And it basically says that the change of xt in time is given by a vector field. So the change of xt in time is given by the change of a vector field plus the change of something that we don't know what it is yet, but I still want to write it down. So what does this notation say? For now, I can just tell you what it intuitively means. The change of xt is given by the change of a vector field. So we're going to the direction of a vector field. Plus, we're injecting some stochastic component now. So like, you can also think about like injecting noise into this equation. And the first component is essentially an ODE. And we're going to see this in a second. But basically, you should think about it as injecting, going into the direction of a vector field, injected with some noise. And in this equation, there's a few things that you probably haven't seen before. The W here is what's called a Brownian motion. And we're going to get to know this object in a second. And we denote this as W. Does somebody know why we call it W? Is that something? Yes. So the answer is why we call it W is because it's also called a Wiener process. And Wiener was a mathematician at MIT. You actually still see some of his pictures at the math department hanging around. There's also, I think, a boost. Like there's like, you see pictures of him still around here. So he was studying that process. So it's also called a Wiener process, and that's why we call it with a W. So now what I want to do is I want to explain what this equation means, go step by step. Any questions at this point? I guess I haven't answered all questions yet, so I'll keep going for now. Okay. Let's see. Okay. Brownian motion. So you should think about a Brownian motion. Oh, it's already there. As something like a random walk. So it's basically, you've seen maybe like a random walk that goes at every step a bit forth and back randomly with equal chance. And it's basically a continuous equivalent of that, but now in continuous space and continuous time. So let's see how we can define this. So it's a stochastic process. We just learned what that is. It gives you random trajectories. In this case, the time can go infinitely long. We don't have to stop at time 1. And it has several conditions. So the first one is that we initialize it at 0. So W0 is just 0. So this Brownian motion will always start at 0, which you can see here on this plot on the right. It starts at time 0. At time 0, it's at 0. The second thing is that what we call, it has Gaussian increments. What does that mean? It means that Wt minus Ws, which is what's called an increment, has distribution that's specified by a normal distribution. And it has this form. So what I took here is I took two arbitrary time points s and t. T is after s. And I say, what's the difference starting from s to the next time point t? And we're basically saying that this has a normal distribution, like a Gaussian distribution, but with a variance that basically increases linearly in time. So let's think about this. If t would be equal s, then it would have 0 variance, because we're just where we are. Like the more further we go in time, the more insecurity there is, the more the variance of this distribution increases. Yes. So third thing is that it has independent increments, and that might be a bit of an unusual condition if you haven't seen this before. So let's define it. Okay, so Wt1 minus Wt0. So what I will now do is I will take a range of increments over time and say that they are independent. So independent means that they're stochastically independent, considered as random variable. You could also say that you basically, they have no information between these points. It's a bit stronger condition than having no information. They're basically saying they're stochastically independent random variables. If you've done probability theory, you will understand what that means. If not, don't worry about it. We will see how to simulate this in a second. So, and I should make the condition that these time points are increasing. So T0, T1 to Tn are increasing in time. Good, cool. If you're taking a machine learning class, maybe you've heard of a Gaussian process. That's a term that's commonly used. And that's a specific Gaussian process. So Brownian motion is a specific Gaussian process. It looks a bit different than the ones you've seen because it's not smooth, but it's a specific, like if you've heard of a kernel from a Gaussian process, this basically what I'm doing is here I'm specifying a specific kernel of a Brownian motion, of a Gaussian process. Got a question? Yes. Yes, so same as the arbitrary stochastic process. So for every draw of W and for every time point, it's going to be a vector in R to the D. So this is a vector valued object. You could, like, great question. So here plotted, it's for dimension 1, for D equals 1. It can be generally defined for arbitrary dimensions. Cool. Let's see. Okay, so with this, we're basically ready to now understand what this other equation means. So I call this the dxt notation. That's not a technical term. That's something I coined it. It basically tries to describe what the symbolic notation is that this SDE describes. So like what the heck does this dxt mean? All right. So first of all, a few fun facts. Brownian motion has continuous paths. Actually, that's one of the conditions. You can impose that condition. You can also derive it. But basically, you can see that if you would draw these paths, you could draw them without ever lifting your pen, which intuitively means what it means to be a continuous function. But these paths are infinitely long. So if I would draw them, I would stand here until eternity because I would never stop. And on one hand, that's just a cool fun fact about it, which is kind of, it basically resembles what's called a fractal. Maybe you've seen this before. So that's just, it's not relevant here, but it's just like a cool fun fact about it. But these really unique properties about these paths make it differentiable nowhere. So you cannot take derivatives of this object. And why am I saying this? Because so far we were studying differential equations, which rely on taking derivatives. So we have to do something if we want to use Brownian motion for specifying a differential equation. We suddenly cannot use derivatives anymore because this object has no derivatives. There's no derivative anymore because the dynamics are inherently stochastic. So that's why the first thing we need to do is we need to basically describe an ODE in a form that does not rely on derivatives. And that's step number 1. So let's do that. So we saw that an ODE is given by something like this. So the time derivative of a trajectory xt is given by ut of xt. And now, what I make the claim is that this is equivalent to the following formula. That xt plus h is given by xt plus h times ut xt plus some error term or remainder term or what I call RT of h here now, which basically, if you take the limit to 0, goes to 0. So what I'm saying is that a trajectory has this ODE is equivalent to that the next time step for some small h, so it means that for a vanishing error term, is this previous time step plus h times in the direction of this vector field plus a reminder term that I can ignore. Maybe you've seen this in other notation. Some people write something like, for this error term, write something like O of h, small o of h, or capital O of h squared. Like this, think about this as a Taylor approximation. Is that clear, or shall I derive that? I can, why that is? I can quickly write it down. So, the answer why that is that we have to think back about how derivatives were defined in the first place. So what does it mean to take the derivative of a trajectory xt? And if you think back to your multivariate calculus class, let's say you have a function like this, big function, and how do we define derivative at a point t? We're taking the next time step t plus h, we're taking xt plus h, taking xt, and we're taking the difference between these two, and then take this what's called differential quotient, and then basically take the limit for that to 0. So what we are saying is that this is equivalent to the limit of h goes to 0, xt plus h, xt divided by h is equal to ut of xt. So far, that's what I've done here is I've used the definition of a derivative. So it's usually not something you use every day, but that's how a derivative is defined. And what we can do with that is we can say this is equivalent to xt plus h minus xt divided by h equals ut xt plus an error term rt of h, which basically means that whatever this term is, essentially, it's like this goes to 0. And now what I do is essentially like do some algebra. I'm just taking the h here, multiplying that with h, and then adding xt, and that's the equation where I'll end up with. So from this equation to this equation, it's just algebra. I'm multiplying with h, I'm adding up xt. All right. If this is not entirely clear, it doesn't matter, because what's going to matter is what's going to come now. This is more like motivation for what's about to come. All right, question? Oh, I'm still in the case for ODEs, but that's a great point. It's going to be random. But for now, it's going to be it's a deterministic term, because we're still in the case of ODEs. But you get your eye is good, because it's going to be random. R is a term I don't specify. R is a term I'm just saying whatever that is. It's just sometimes something that goes to 0 when I make h go to 0. So it's just like if for very small h, it's going to be essentially 0. All I'm saying is that's an error term that you can effectively ignore. That's basically what I say. Good, cool. Okay, so now we're going to make this random, and now we're going to do the same thing as before, and I'm going to write down now this notation that I've used for the SDE. So what I've done now, instead of writing down an ODE, I've wrote this SDE down. And I'm doing now the same thing when injecting noise into this formula. This formula we cannot generalize really, because it's like derivatives. We don't know how to do this for stochastic processes in this form, but we know how to do this for, like, this is a form that does not rely on derivatives. Right? I told you we need something that does not rely on derivatives. That's something that I'm not telling you what a derivative here is. I'm just saying that, like, the next time step is specified by this plus some negligible error term. And now I can make this random. So what I can do, I can say xt plus h is given by xt plus h times ut xt plus, and now that's the new term that I want to highlight in color, sigma t, and now the Brownian motion comes in, wt plus h minus wt. And I still need the error term plus h times error term, and great point, this thing is going to be random now. So what does it mean for this to have order 0? It means that its standard deviation goes to 0. We need to, like, this is a random object, cannot deal with the fact that it's Whoop. So what's written here is that the expected square norm and the square root of that is going to 0. So let's recap. We knew what an ODE is, that we specified with derivatives. We found a formula that is not relying on derivatives, but that relies on just going a step forward in time, h, that's rather small, and we can specify that up to an error term, RTH. The right-hand side we can make random. That's something we can inject noise. An idea of this notation is essentially to add noise to this equation. So we say that the next time step is the previous time step plus some h given going into this vector field plus some increment from a Brownian motion, which is effectively noise, that we scale now by the diffusion coefficient sigma t. So the more, if sigma t is 0, this is just 0. And if sigma t is 0, what have I written down? An ODE, exactly. So like if sigma t is 0, that's just that. And we've learned that this is equivalent to this, which is an ODE, right? So for sigma t bigger than 0, I've added a term that I told you is a Brownian motion. And I'm basically adding this on top of that, plus some negligible error term. Okay, and that's essentially what this notation means. That's how you should think about it. I'll show you, to be honest with you, most of the time I think about actually an SDE as something how I would simulate it, and I will show you that in a second. But this is basically, you could think about this as a Taylor approximation. It's not really a Taylor approximation of this thing, but this equivalent statement in the same way that this is equivalent to this is equivalent to this. Maybe let's compare quickly about like ODEs and SDEs again. So we've seen ODEs have trajectories as solutions. What's the solution of an SDE? It's a stochastic process. It's a random trajectory. To define an ODE, we need a vector field. To define an SDE, we need a vector field and a diffusion coefficient. So we need an extra component. An ODE is basically defined by a derivative and an initial condition. So it says that the derivative of xt is given by the vector field. The SDE also has an initial condition, and it says that the direction of xt, or small incremental changes of xt, are given by small directions in the step of a vector field, plus small noise or steps added from a Brownian motion, like small increments added from. So we're injecting stochastic noise in there, which essentially says that we impose a condition on the stochastic process, which basically says that this holds. So I've not told you that this thing exists. I've not constructed it to you. I'm just saying this is a condition that we impose. Question?
Where is W being sampled from?
Yes. Yes. At this point, I've just brought you down math. I didn't give you an algorithm yet. So the question is like, how do we sample from this, right? And that's a great thing for the next step. Thank you. So basically, what is the distribution of this object? I wrote this down. Let's look back. The distribution of an increment, what I use here, is given by a Gaussian variable with variance of the difference in time. The difference in time of these two things is h. So this object has distribution, has a Gaussian distribution with variance h, or with covariance matrix like h times the identity matrix. So to sample from this, you would sample from this distribution, which is something we know how to do. Okay, I'll show you an algorithm in a second. So now we do the same exercise that we did for ODEs, for SDEs. So if I show you this equation, and I'm claiming I'm imposing a condition on something, I should tell you, does it have a solution, and is that solution unique? So, and basically the same thing as before holds. So if the vector field ut is continuously differentiable with bounded derivatives, then a unique solution to this SDE exists. More generally, again, if you know what a Lipschitz condition is, means that this SDE has a unique solution if this vector field is Lipschitz. The key takeaway is, in the cases of practical interest for our purposes, there will be unique solutions to this equation. So there will be an exactly one stochastic process that satisfies this condition, or in other words, satisfies this stochastic differential equation. So you can assume that whatever you write down in such a form will have a unique solution. If this was a stochastic calculus class, which is not, we would try to construct this now explicitly. There's a thing what's called like stochastic integrals, and you can construct this with like the same way you construct Riemann integrals with Riemann sums. You can find something like a Ito-Riemann sum and then construct this explicitly. For the purpose of this class, this is like an equivalent statement. I just haven't shown you yet that I have a solution to this. Good, cool. So thank you for the question about simulation. So we now need to think about like, that's something we can plug in a computer. How do we sample from this? We know that this is a normal distribution with variance h, and we know how to sample from it. So now let's iterate that and arrive at an algorithm that's called the Euler-Maruyama method, essentially an extension of the Euler method that we've seen before. So it basically describes how to sample from an SDE. So what have we given? We've given a vector field ut with a certain number of steps, and we have a diffusion coefficient sigma t. We start at time equals 0, and we want to simulate until time 1, so our step size will be basically 1 divided by the number of steps. We set the initial condition x0 to be 0, so we're imposing the condition we have, the initial condition I have written above here. And then we loop over the number of steps. We draw a sample from a Gaussian, standard Gaussian. So like, basically, you could call it some Python package. If you do this in Python, and you say the next time step xt plus h is given by the previous time step plus h times ut of x. So until that time, it's just ODE simulation. And now what we're doing is we're adding some noise. So we're scaling the standard Gaussian with square root of h. Why square root of h? Because we want to have it variance to be h. If I scale a variable with variance 1 with square root of h, its variance will have h. Variance scales quadratically. That's why we need square root of h. And then we need to scale it by the diffusion coefficient sigma t. And then we loop over this over many time steps to arrive at the final trajectory that we can then return. And you'll implement this in the lab. So if you have questions, best to ask now. Yes?
So do you mind just repeating what objects haven't defined?
Oh, to make this completely rigorous. So if you would take a stochastic calculus class, what you would need to do, first of all, you would need to show that a Brownian motion exists. There's like a diversity of different construction methods. That's not trivial. And the second thing is then you need this construction that I mentioned with the Ito-Riemann sums. You need to explicitly construct a stochastic integral, and then you show that this is basically fulfills that condition. That stochastic process exists, yeah. So you construct it explicitly with a Brownian motion, and then you have these Riemann sums, or Ito-Riemann sums, and then you need to define what it means to converge in this space of random trajectories. This is not trivial. And then you arrive at something that fulfills this condition. Sigma, yeah, so sigma t, okay, we're not going to do this, but this is a great question. So sigma t can be a function of x. I actually written a paper on this, so you can do this. You can also learn it. But we want to teach you here the state of the art that's currently at the frontier and leave out some exotic stuff. So that's why we're not doing this. But great point. We can make it state dependent. Yes, great question. So I said that we need to add this increment, and I'm telling you that the increment has variance h, so h times identity matrix. And I sampled here something with variance 1. So, and if I scale it with square root of h, its variance will scale with square root h squared, so which will be h. So it's a bit intuitive at first, why square root of h. But it's because we want to have the variance increasing linear in time, not the standard deviation. Kelly?
On the previous slide, you said that that theorem says there's like be the solution? Like, it seems like there's a lot of possible
Yes.
trajectories. So what does it mean for there to be a unique
Yes.
solution?
Yes. Okay. So question is, what does it mean to be a unique solution? So you're right. There's many different trajectories, but I told you the stochastic process describes the distribution of these trajectories. So now, to actually formally define this, what I would need to do is that we need to define what's the distribution over trajectories. For that, you need measure theory. You need to define like a whole bunch of technical things that, like, I think is not necessarily needed for actually doing machine learning. But you need to define that, and then you say that these distributions that you then define over this space of trajectories would be same. So as you can imagine, it's not quite. I could spend a whole class on this, which I'm not going to. Cool. Okay. But the way to think about this is the way you think about this. Really, like when I think about SDEs, I think about something like in this format. I go to the next step in the direction of the vector field plus adding a bit of noise. And as soon as my vector field is nice enough, this thing has a unique solution. Good, cool. Let's consider an example. So I showed you before the example of a linear vector field, and now we're just looking at an equivalent construction of that, but for stochastic differential equations. So what I'm doing is I'm saying my vector field is minus theta of the state xt. So we've seen this before. But now we're saying we're adding a constant diffusion coefficient. So sigma is just a constant in time. So that's going to be every time I'm going to inject the same amount of noise. And that's called an Ornstein-Uhlenbeck process. You might have seen this. I think it's a Danish scientist who found this. And it basically describes this linear ODE, so this exponential decay that we've seen before, but now with some noise injected. So if we have zero noise, if sigma is 0, we just have an ODE, right? So like if this sigma is 0, we've learned already that the SDE just basically reverts back to the ODE case. And this is the plot I showed you earlier. And now you see if I increase the diffusion coefficient over time, you see there's more and more stochasticity that I'm injecting into this process. You go from left to right, so you get more and more noise. It's going to be more and more random. And that's basically what this process describes. It's kind of this exponential convergence to something, I'm just going to state that now, to a normal distribution with that's specified, with variance specified by these two parameters. You'll actually implement this in the lab, so you'll see these plots appearing. Good, cool. All right, so now we're finally ready to define what a diffusion model is. Okay, and what I'm going to do, I'm going to override the definition of a flow model because the changes are pretty minimal. So I'm going to make the changes in green. So what is a diffusion model? I told you that we want to do generative modeling, which means we want to convert an initial distribution that you should think about as a Gaussian into a data distribution. And a flow model does this with an ODE. And now we're just going to do the same thing, but with an SDE. Okay, so the goal is to use a stochastic differential equation to convert a simple distribution, something like a Gaussian, into a complex distribution. In the same way as before, the key ingredient will be the neural network, and the neural network will be the vector field. So the same way as before, that has not changed. And then we add a diffusion coefficient. Let me add that here. And it's basically like sigma, like t, in the same way as I had before. So like this diffusion coefficient is just basically what I wrote here. And it's important to note that most of the time, that's fixed. So we're not going to learn this. There's not going to be a neural network for this. We're just going to have a formula for this. So you don't really have to worry about the sigma t at this point. You can actually more like later choose it the way you want it, which is what we're going to see. So the diffusion coefficient is not going to go to learn. We are still going to learn the vector field. It's very important to note. So really the core ingredient is still going to be the vector field. The same way as before, we're going to randomly initialize the model. But now, we're going to simulate an SDE. So what we're going to do, instead of simulating this ODE, we're simulating the same way an SDE. Let's keep this in green. Can you see this at the back? It's in green. I can also switch it to, you can see it. Okay, good. So what have I changed? I've changed the introduction. On top of having a neural network that represents a vector field, I also have a diffusion coefficient. In the same way as before, I'm initializing with my initial distribution, P init, and then I'm simulating an SDE in this way, which we know how to do. And the goal is that we end up with the data distribution, which is the distribution of objects that we want to generate. Question?
I would imagine by adding this noise term and basically by adding more degrees of freedom, it might make this model harder to train. So if you want to add, is that the case? And also, if you want to add your own kind of conductive priors, is putting all the weight on training a really good neural network enough, or to practice, could you even like add terms to this SDE right now as well?
Yes, great question. So the question, like, I was asking, like, what is the effect of adding this term? So first of all, I should say that's why I said the flow component is the most important to understand. Is that many state-of-the-art models are just flow models. Like, it's the really crucial part is the flow part, and then you can add in stochasticity by this. And there's a bit of it's both an empirical and a theoretical question. So most people just empirically choose this sigma t in a way that serves best. There's a bit of a trade-off, is that you explore more if you inject more noise. In some sense, you move more through space. But also, if you do it too much, you get some numerical errors that you might incur and then not generate as nice objects. Yeah, great question. So why are we doing Brownian motion, right? Like it seems kind of arbitrary. So there's several answers to this question. So first of all, a Gaussian distribution is something nice. Like Gaussians, like we know from the central limit theorem, for example, that Gaussian distributions are somehow universal, and we want to have a process that has Gaussian increments. So Gaussian is somehow, we want to most of the time anyway, so Gaussian is nice. But it's actually more than that. It's pretty universal. Any Markov process that is continuous in time and has continuous trajectories actually will be represented by an SDE in this form. So like you can impose relatively weak assumption and reduce it to this stochastic differential equation. It's like whenever you have non-Gaussian increments, or not in this format, you're going to have things like jump around in space. They're not going to be continuous and stuff like that. So it's going to be significantly more ugly. So Brownian motion, it's that sense. The way I think about Brownian motion, like I think about a Gaussian distribution as something really universal for distributions, and a Brownian motion, I think about it as this equivalent for stochastic processes.
Are there diffusion models that like replace the Brownian motion with just like a general Maruyama?
You could think about general Markov processes. That's correct. I've actually. It does not reduce like this. I actually wrote a paper on generalizing this to Markov processes, but I'm here to teach you as I said, the state of the art and not the exotic research. But you can make this more general. But then, as I said, you will have jump processes. You will have something that's not continuous. It's going to be more ugly. Well, more ugly. I would say nicer, but more difficult.
Maybe this is also like an annoying question, but when we define like SDEs in this way, is there stuff that like breaks down or goes wrong if we choose a different Gaussian kernel which is differentiable?
Yes. So you're saying if you look at this as a Gaussian process,
yes.
So like a Gaussian process. Now I'm lacking space. So usually. So this is a detour. You don't need to understand this. But a Gaussian process is usually specified for some sort of mean function and a kernel function k, right? So like if you've taken a class, like k was like what's a Gaussian kernel. This is a specific kernel. So there's other kernels that would make the function smooth. It's called the RBF kernel, for example. There you just have, these are just smooth trajectories. So this would reduce to the ODE case. They would be random, but they're smooth. That means you've not done anything new. And there's other stuff that you could do, like white noise, but then they would not even be continuous. That would be just completely. So you could do other choices.
Can you ask me also why SDA as a topic?
No, I guess I'm just curious if people are interested in defining like SDEs instead of using linear processes, using Gaussian processes with smoother kernels.
Yes, it's just that if they're smooth, you could basically they're smooth functions. So then says you've not done anything new. That's true, but we've also done this with the initial condition of the ODE. So I'm not saying it's not possible. I'm just saying why it would not be qualitatively that different than what people done. Cool. Okay, so we're almost at the end. So let's think about how we sample from a diffusion model. And this algorithm is essentially the same thing as before. We're basically saying we're using the Euler-Maruyama method. We initialize the point now in a random way, not in a deterministic way anymore. And at every time point, we do the same thing as before. We draw a Gaussian sample and go a small step into the direction of the vector field, plus adding some Gaussian noise scaled by square root of h and the diffusion coefficient sigma t. And you're going to implement this in lab 1. You're going to see. And also important to note, we're always only interested in the final time point x1. That's what we want to reduce. All right, cool. At this point, we're at the end. Ezra, you wanted to say something, right? You wanted to grab the mic?
Yeah, so let's just finish by talking about some of the logistics of this class. What do you have to do to pass this class? You have to come to the lectures, or if you can't make it, you can watch the recordings, which I think will get posted maybe with like a day delay, and do the labs. We want you to pass the class. I think you have to give us an excuse to not pass you, but really it's not anything super complicated. Come to lecture, pay attention, do the labs, and you should be fine. Tony? Will there be a piazza? We do not have a plan to, there's currently no piazza, and we have, okay, so you can email us. If we get like 100 emails, maybe we'll have, we'll think about it. For now, there's no piazza. Right, okay, so yeah, so at the end of the day, this is described on the website in our logistics section. There are 25 points in the class. Lecture, 10 points. Labs, 5 points each, 15 points total. Total of 25 points, and you need 18 points to pass. I think what we have written down right now. And then, yeah, so in terms of resources for this class, the central backbone, kind of your main point of reference should be the lecture notes, which you can find on the website. These are self-contained in a way that the slides are meant to accompany the lecture, and in that sense, they're harder to view kind of standalone, but the notes are complete and elaborate on many of the points that Peter went into depth about, and many of the questions that people asked. You can find answers there. And then secondly, office hours. You can come to office hours to ask questions about lectures. I think they're primarily intended for help with the labs. So yeah, I think with that, I'll just say that we're releasing Lab 1 today. I think it was actually released at like 11 p.m. last night, but it's available on our website. You can go to diffusion.ccl.mit.edu, the website up there. You can open up the lab. We are basically providing a link to GitHub. So you can download it from GitHub. You can open it up in your favorite Jupyter Notebook environment, like Colab, fill out do the assignment, export it to a PDF, and upload it to Gradescope. This is going to be due on Friday at 5 p.m. And yeah, so try and start it as soon as possible. I think we have office hours tomorrow at 3:30?
3 p.m.
Okay, my bad. 3 p.m.